So here's more or less, oh, I haven't yet put the slides on this site, but I will. I want to talk about making unitary representations of real groups, and the three big ways to do that: real parabolic induction, cohomological parabolic induction, and unipotent representations. So that's the topic. So as with Jeff, I'm going to assume that you already know what the most important, interesting problem in mathematics is. And that means understanding all the ways that a group can act as automorphisms of a Hilbert space. The reason it's interesting is that mathematics is full of interesting Hilbert spaces. Gelfand in the 1930s said that it was good to solve this problem for locally compact groups. Mackey in the 1950s said that you could analyze this problem in terms of normal subgroups of G. You could make reductions. And so more or less, you should just consider simple groups. Many people over many decades understood that the setting of reductive groups was really wonderfully suited to include simple groups and to be stable under inductive arguments. So that's the setting where I'll work. I want to talk about the unitary dual of a real reductive group. So as Jeff said, I've been working on this problem for a long time without complete success. So what I want to talk about today is the pieces of the ideas that I've gotten from Jim. Okay. So the abstract mentioned this conjecture, and so I sorry. Yeah, these things, it's always hard to know who's responsible. Anytime I talk about where an idea came from, George Lustig tells me, well, no, it came from me. So Jim has this sort of dual attitude. I must say I know which one I like better. Anyway, so here's a very precise conjecture. If G is a real reductive algebraic group and pi is a unitary representation having integral infinitesimal character, then pi is an Arthur representation. So I asked Atlas if this was true for the symplectic group of rank 6, and Atlas said that it was, and you know, lots of other smaller classical groups. I think it's likely that it's true for classical groups. And well, I also asked Atlas about G2 and E6, and it's true. In F4, what Atlas says is that there are two unitary representations of integral infinitesimal character, which might not be Arthur representations. Well, and for split E7, 6, and for split E8, 27, another small three-adic number. So why do I say it fails for at most these cases? So for exceptional groups, Adams and Barbash and I gave a definition of Arthur's packets, but the definition is quite difficult to compute. And to be completely honest, we don't completely know how to compute it. And so we have in the Atlas software a function which will compute as much as we know how to calculate of Arthur's representations. And I can plug it in and say, here's split F4, tell me all of the Arthur representations that you know, and it spits out this list. And then I can ask it, tell me then all the unitary representations, and compare the list. And well, there's these two that are missing. But we don't absolutely know that they're not Arthur. So, well, as I say, we have a list of Arthur's representations that's nearly complete. Jeff did some calculations. We have these wonderful little Zoom meetings twice a week of Atlas people, so that we all have an opportunity to make complete fools of ourselves often, and we get to enjoy it, sort of. And Jeff did some calculations in an Atlas meeting which seemed to prove that those two F4 unitary representations are not Arthur representations. So if Jeff's quick and dirty calculations were correct, that proves that the conjecture fails for F4, and in fact, many, well, split E7, split E8. I did check complex F4, and the conjecture is true. Yeah, the point is that for complex groups, it's much easier to define Arthur's packets. And we know exactly how to do that. And so, yeah, for complex groups, we can precisely calculate Arthur's packets, and we get exactly the same as the unitarity calculation predicts. Okay, so that's more or less all I'm going to say about this conjecture. I do think it's interesting. Well, if Jeff's calculations are right and these unitary representations are not Arthur, then it's a really interesting question. Why are they unitary? Where do they come from? That would be great to sort out. If Jeff's calculations were wrong, then it would be great to really figure out, in other words, if these two representations are Arthur representations, then it would be great to really understand how to compute his packets in exceptional groups. Okay. Yes. So Arthur's packets have the property that it's possible to make a stable combination of representations by summing appropriately over the packet. What Jeff showed was that you could not make a stable combination of representations, including these, in the case of F4, these two potential counterexamples, you couldn't make a stable combination of unitary representations in which they appeared. That, yes.
Sorry, but this wants me to a question I will say for the end. Doesn't Arthur tell you exactly, if you assume everything about the trace formula or the trace formula, doesn't he tell you exactly what the local Arthur packets should be?
No.
No.
I mean, yes, in the case of classical groups, but certainly no in the case of exceptional groups.
So even if Jeff's calculation is correct, it could be that these representations belong to an Arthur packet.
That's the other possibility, yes, that the Arthur packets could include non-unitary representations where the stability happens, and that would be a fascinating thing to understand as well. Okay, good. So what I want to do today is talk about three fantastic ideas. I learned early on. Well, my father was a preacher, and there were two things about sermons. You should talk about big ideas, which are great, and which are not yours. And so the first big idea that I want to talk about is real parabolic induction, more or less put into the world by Gelfand. Cohomological parabolic induction, put into the world by Greg Zuckerman, and unipotent representations, put into the world by Jim Arthur. And again, in the philosophy of preaching a sermon to you, and I'm going to show how these ideas nearly compute Arthur's packets. But I also want to mention that these three big ideas come from three different countries, one of which no longer exists, one of which may not exist much longer, and Canada. So I will stop and repeat a story which many of you have heard me repeat many times, which was I went to a conference in Lumini about 40 years ago, and one of Jim's sons was about maybe 5 years old, and he struck up a conversation with me one day, and he said, my country is bigger than your country. And I said, yes, that's quite true. And he said, my country is more beautiful than your country. And I said, yes, you certainly have a very beautiful country. But this was Jim's son. And so he realized that the trend of this conversation was perhaps not entirely polite. And he said, your country has a bigger army than my country. Anyway, so I said that representation theory was useful because it concerned all the ways that a group could act on a Hilbert space. So what you want to do is find a small collection of actions of a group on a Hilbert space which magically is everything. So a sort of more elementary sounding problem of the same nature is find all the ways that a group can act transitively on a space. So that means conjugacy classes of subgroups of G. And that is, of course, a horribly difficult problem. There are too many subgroups to make interesting statements, but here's an interesting statement. If H is an algebraic subgroup of an algebraic group G, then you can find a deformation, a limit of conjugates, H0 of H, so that H0 is a normal subgroup of a parabolic subgroup of G. So, deformations are not isomorphisms, but a lot of properties get preserved in the deformation. I'll mention, in the case of a real reductive group K, this group K can be deformed to Mn, which is normal in MAN. And this deformation is at the bottom of Harichandra's analysis. It's a really important idea. So, okay, so this theorem is a nice model. I couldn't find a reference for it, but anyway. So anyway, this impossible problem of describing all subgroups gets related to the reasonable problem of describing normal subgroups of parabolic subgroups. Okay. So what's the big picture in representation theory? Suppose you've got a, I'll stay for the moment in the complex world, a parabolic subgroup of a reductive G. Then the quotient variety is projective algebraic. That's the definition of or one definition of a parabolic subgroup. It's a subgroup so that the quotient is projective variety. This parabolic, like any algebraic group, has a unipotent radical, a unipotent normal subgroup, and the quotient of the parabolic by the unipotent radical is a smaller reductive group. If you have a representation of that subgroup, LOC, that gives you an equivariant vector bundle on G mod P. And Gelfand's idea is that the space of sections of that equivariant vector bundle is a representation of the big group. So this is a way to go from representations of the Levy subgroup to representations of G. And exactly what I mean by representations is, well, in this theorem, I might mean algebraic representations, but the theorem is also true if I mean quasi-simple representations. There's the theorem that if you start with an irreducible representation on the Levy and form this equivariant vector bundle, take the space of global sections, then the space of global sections is almost an irreducible representation of the big group. And every irreducible representation of the big group arises in this way. So the nearly is, oh no, the nearly is there's still a lot of room for difficulties there, but that's a nice theorem. So I said all that about complex things, but if G is a real group and the parabolic is defined over R, then this real quotient G mod P is a compact manifold, and a unitary representation of the Levy subgroup gives you a Hermitian vector bundle on that compact manifold. The space of L2 sections is then a Hilbert space, and that space of L2 sections is a unitary representation of G. And what Gelfand and Harishchandra proved is that if pi L is nearly an irreducible unitary representation of L, then pi G is a nearly irreducible unitary representation of G. The nearly refers to the irreducible. The unitary is absolute. So that's great, but it's very far from true that this is all of the irreducible unitary representations of G. So the moral of these slides, see, it's all about a sermon. The moral is that a unitary representation of a Levy subgroup is giving you a unitary representation of G. That moral just needs a real Levy subgroup, but not every real Levy subgroup comes from a real parabolic. So a Levy subgroup of a real parabolic is the centralizer in the real group of a split torus. Suppose instead you've got a parabolic which is opposite to its complex conjugate. So it's as far from being real as possible. Then the intersection of P with its complex conjugate becomes a Levy subgroup, and it's defined over R. And so that intersection is a real Levy subgroup, but not a Levy subgroup of a real parabolic. This P of C defines a G invariant complex structure on G of R over L of R. So I will what happens is that this G of R over L of R embeds in G of C over P of C. And this gadget is obviously complex. And what's obvious is that this is an open subset. So G of R mod L of R becomes an open subset of a complex manifold, so it's a complex manifold. Okay. So a Levy subgroup like this is the centralizer in G of R of a compact torus. This time, if you take a unitary representation of such a Levy, you get a holomorphic Hermitian vector bundle on this quotient space, G of R mod L of R. So the natural place to look for a unitary representation would be on L2 holomorphic sections of this vector bundle. But that space of L2 holomorphic sections is almost always 0. Harishchandra in 1954 found essentially all the examples where the space of L2 holomorphic sections is non-zero. And that's how he constructed the holomorphic discrete series of G. So it's interesting and important, but it's not nearly exhaustive. By the way, this is another example of the way mathematical credit gets distributed. If you try to look in the literature to find where the Borel-Weil theorem is proved, the answer is that it's proved in this 1954 paper of Harishchandra, and that's the only place. I mean, in the original literature. But anyway, there was a Bourbaki-Talk, and I mean, the Bourbaki-Talk was only about the case of compact groups, and you know, Borel and Weil had certainly worked it out in that case, but it was Harishchandra. Anyway, so actually worrying about Harishchandra's being mistreated is not one of the things you should lose sleep over at night. So Harishchandra understood that there should be a more general way to get unitary representations in this setting, but when this L of R is centralizer of a compact torus. And in particular, in the case when L of R is a compact torus, then Harishchandra managed to find unitary representations. But the proof was extraordinarily indirect. It's an amazing piece of mathematics. And it's just monumental and amazing, but you can't point to it and say, oh yeah, L2 holomorphic sections. No. So around 1965, shortly after Harishchandra had found these representations, Costant and Langlands suggested that the way you should get a representation of G out of this holomorphic bundle was by looking at higher Dolbeault cohomology. So there aren't holomorphic sections, or at least not L2 holomorphic sections, but maybe there's higher cohomology. So, okay. So I want to say a little bit about the geometry. So I'm in this setting where complex parabolic is opposite to its complex conjugate. I'm going to use the word theta stable. I don't know. And the real levy that you get in this way. So here's an example. Suppose I take G of R to be GL2N R and L of R, excuse me, to be GLNC. Then you know, I'm sorry, that GLNC is the centralizer in GLNR of multiplication by I. So R2N looks like Cn, and so there's this linear operator of multiplication by I, and if you take the centralizer of that linear operator, you get GLNC. So this X can be thought of as the space of complex structures, linear complex structures on R2N. That's a complex manifold of dimension n squared. It has in it a compact complex submanifold, O2n divided by UN, which are the orthogonal complex structures on R2n. And that compact complex submanifold has dimension n squared minus n over 2. All these calculations of dimensions of spaces were done by Atlas. When I was young, I could do them in my head, but now I just, yep, that's the answer. So that's fine. Now, in the old days, people learned about Stein manifolds. And Stein manifolds are complex manifolds that are designed to have a lot of functions on them. So one of the things Harishchandra did was to prove that in the Hermitian symmetric case, G mod K is a Stein manifold. And a feature of Stein manifolds is that the only compact subvarieties they can have are finite. So this manifold X has a compact submanifold of dimension sort of half the dimension. So it has no chance to be Stein. But what Wilfried Schmidt proved was that X is S plus 1 complete. The definition of Stein, well, I'm not going to recall the definition of S plus 1 complete, but a Stein manifold is 1 complete. And so what S plus 1 complete means, it's as close to being Stein as you can get with this big compact subvariety. So there are vanishing theories. On a Stein manifold, Dolbeau cohomology vanishes in positive degrees. On a S plus 1 complete manifold, Dolbeau cohomology vanishes above degree S. So Dolbeau cohomology in degree S is a right exact functor going from holomorphic vector bundles on X to vector spaces. And there are precisely analogous results for any parabolic opposite to its complex conjugate. Okay, so
Sections are Hilbert space?
no, they're a vector space. I mean, it's like, well, in the case of a Stein manifold, we're just talking about holomorphic functions. And well, when I was trying to make a Hilbert space, I was trying to take L2 sections. Here, it doesn't make sense. The Dolbeau cohomology, the natural invariant forms on the, whatever you call them, the part, there are these things indexed by P and Q, the wedge P, tensor wedge Q of something else. And the forms on those spaces are not definite. So it doesn't make sense to talk about L2 forms on on these spaces.
Other hand, you may add coefficients there, right?
Yeah, but I mean, the S+1 complete allows coefficients. I mean, the statements about vanishing allow coefficients. Okay, so what does this suggest? So you've got this complex manifold G mod L, and there's an exact functor which goes from a representation of L to a holomorphic vector bundle on X. And then Schmidt's theorem says that if you take this top degree Dolbeau cohomology, that's and I have a typo. This L is supposed to be a G. The pi L is a representation of L. This space over here is a vector space with a G action. And because of the vanishing above degree S, this is a right exact functor. But there's all kinds of problems. This Dolbeau cohomology can be defined as the kernel of some D bar operator modulo an image of a D bar operator. Well, the kernel of the D bar operator has some nice Fréchet topology on it, no problem. But the image of the D bar operator, well, the D bar operator is continuous, but the image of a continuous map on Fréchet spaces, who knows what it is? It's at any rate, it's certainly not obvious that it's closed. And so the natural topology on this Dolbeau cohomology is not obviously Hausdorff. So that's a problem. Even if you can prove that the image of D bar is closed so that there's a natural Fréchet structure on the Dolbeau cohomology, it cannot carry a unitary structure. And the possibility of lower degree cohomology means that this functor is not left exact, so it's not exact. So these are the problems. So Zuckerman to the rescue. So what those problems that I just stated, those problems are all about analysis, about the image of some differential operator being closed, for example. And that's an analysis problem. And analysis is hard. So what Harishchandra in 1953, I would like to take credit for this result, but unfortunately I was born in 1954. So Harishchandra showed that many representation theory problems are equivalent to algebraic versions. So Jeff alluded to this. The basic problem we're talking about here is finding a way for G to act on a Hilbert space, preserving the Hilbert space structure and not leaving, having exactly two invariant subspaces. That's a deep analysis problem. Harishchandra showed that that was equivalent to the algebraic problem of making a GK module with a non-degenerate positive Hermitian form and exactly two submodules. So that's the kind of thing that Harishchandra proved. And so this Dolbeau cohomology idea, which is technically inaccessible, Zuckerman found an algebraic version of it. So what did he do? So Dolbeau cohomology involves this sheaf of germs of holomorphic sections of some vector bundle. Zuckerman said you should replace that by formal power series sections of the bundle. So in algebraic language, that's some produced module. And instead of the global sections functor on sheaves of holomorphic things, you have just the functor of taking k finite vectors. So using those two things, Zuckerman made cohomological induction functors, which went from Harichandra modules for L. Oh, and again, I have a misprint, damn it. This L intersection K should be K. And that's egregious. I think that's egregious enough that I want to stop and fix it. Oh, shoot, did I already close? Ah, no. Good. Oops. To GK. Good. Oh, shoot. Here we go. Thank you. And I have somewhere there's a window. Yes. Good. Yeah. I knew you'd be pleased. And Zuckerman. I'm sorry. There, yes. Okay. Okay, yes. So now his functors really go to GK modules. And to say what's true about them, I'm always going to twist this holomorphic thing by a square root of a canonical bundle. This is like the row shift in real parabolic induction. And it causes a little bit more trouble here, but I just want to ignore that. So these functors, there should be things like that for any rational levy in a p-adic G. And I don't think there's any general result of that nature. There's a lot of cases where things are known, but it's, I think it's a really important question. Anyway, so what? Oh well. Okay. So here's the nature of Zuckerman's results. So I've still got this theta stable parabolic. And I want to fix a cartan in the levy. And I want to decompose that cartan as the center of the levy, direct sum its intersection with the derived algebra. So the Z stands for center, because we all know that Lee wrote in German, and the D stands for derived. Probably it stands for dérivé because we're in Canada. So it's bilingual, German and French. So suppose I've got a representation of L, and it has infinitesimal character, which I'm going to break into its central part and the derived group part. So the central part, and the L is extra there, is just the character of the representation on the center of the Lie algebra. So here's what Zuckerman proved. He showed that each of these derived functor modules is a finite length GK module of infinitesimal character exactly the same as the one on L. So that's just like real parabolic induction. And if gamma is weakly non-positive on the co-roots of H in the unipotent radical, then you get a vanishing theorem. These derived functor things are zero for I smaller than S. And if in addition to this non-positivity, the representation you start with is unitary, then you conclude that this RS of pi L is also a unitary representation. So that's nice. So now I want to just assume not that this whole gamma is non-positive, but just the central part. So if that central part is non-positive and pi L is small enough, then you still get the vanishing theorem and you still get preservation of unitarity. So the relation between these two conditions is technical and hard to get your head around. I'm going to write some examples on the next page, the next slide. So what I need to tell you is exactly what small enough means in this last condition, and how this leads to constructing Arthur's representations. Okay, so what about these positivity or negativity conditions? So I was looking at two things. One, gamma being anti-dominant on the co-roots of U, and second, the central part being anti-dominant on the co-roots of U. So to see what these conditions look like, and I lost a left parenthesis here. I'm much better at using Emacs than I used to be because Mark van Leuven makes fun of us every time we misuse Emacs. But as you can see, I mean, if I properly used Emacs, I would never mess up a parenthesis. But all I can say is it's better than it used to be. So I want to take this example of a Levy subgroup, GLN cross GLN in GL2N. And the representation on the Levy I want to take is the trivial on the first GLN twisted by some power of determinant, and the trivial on the other GLN twisted by some other power of the determinant. So this is a really familiar kind of thing in all kinds of representation theory. And if I use some standard basis for CN, where I call the first n coordinates the EIs and the last n coordinates the FJs, then the co-roots of H and U are the EI minus FJ. So the infinitesimal character of the representation I've written has a central part, which looks like this A coming from the determinant, and the infinitesimal character of the trivial is written over here. And so now you can see immediately, what did I think I changed this, I meant to change this to dominant. That here, I don't know, just to make it more familiar, I wanted to change this to dominant instead of anti-dominant. And so if you ask for dominance on the co-roots of U, it means that A minus B has to be at least n minus 1. And condition 2, dominance of the co-roots just on the center, that's very easy. It's A minus B is greater than or equal to 0. So condition 2 is weaker. And I mean, that's nothing special about this case. Condition 2 is always weaker, independent of what you have for pi L. So in the world of rational parabolics, convergence of intertwining operators in this picture is guaranteed by the strict condition 1, and I should have erased that's why I wanted to erase the anti. The intertwining operator will converge if A is much bigger than B. Or if the representation you have on the levy is tempered, then the intertwining operators will converge if you just have this positivity A minus B greater than 0. So the point of this slide was to try to connect the kind of positivity things that are coming up in Zuckerman's theory with more familiar positivity things. And Laurent and Arthur are saying, well, except he's lost a factor of pi over 2, and there's the epsilon factors, and it's not even close to true. But anyway, as far as I understand, this is. Oh. Yes. So yes, the convergence of the intertwining operators is dominance with a strict. Yeah. Yep. Okay. And here also a strict version of 2. Okay. So this was just aside. So what about small enough? So in this convergence of intertwining operators, you get extra good behavior if the representation you're inducing from is tempered. What about cohomological induction? What makes that better behaved? So I defined weakly unipotent to mean that if you start with a representation pi and you make a coherent family out of it, then nothing in the coherent family can have smaller infinitesimal character. So so the trivial representation has that property. If you make the coherent family of the trivial representation, everything in the coherent the trivial representation has infinitesimal character rho, and the coherent family consists of virtual finite dimensional representations. So the infinitesimal characters are all highest weight plus rho, which is bigger. So the trivial representation is a minimum. If you have a representation of infinitesimal character 0, not surprisingly, that's smaller than anything in its coherent continuation. And the interesting case is that if you have a real Arthur parameter, which is trivial on the C cross, and I wrote A because my brain doesn't work anymore. I should have written capital pi here. A of psi is some component group, I think. So this is meant to be an Arthur packet, pi of psi. And the statement is that everything in it is weakly unipotent. Okay, so what the version, the theorem I wrote in writing about cohomological induction is that if the central character is weakly, I should have written, I've gotten all these positive things backwards, non-positive on the co-roots, and the representation on the levy is weakly unipotent and unitary, then you get a vanishing theorem and preservation of unitarity. So, so what that says is that weakly unipotent unitary representations on theta stable levies can always be cohomologically induced, and this cohomologically induced is extra. This is the slide that I wrote at 4:30 this morning. They can always be cohomologically induced to unitary representations. All you have to do is choose the P that makes the central character weakly anti-dominant. So yeah, the non-negative anyway. Okay, so that's, I wanted to go on and say in more detail how you construct Arthur packets, but I think I've given hints. You construct Arthur packets by taking the Arthur parameter, making a Levy subgroup with it, somehow the centralizer of the C cross on the dual side, and then the dual Levy subgroup in G. And that Levy subgroup that you get will, well, I'll write a few words. Well, this Levy subgroup defined by the Arthur parameter. This is the kind of picture, and down here you have a unipotent representation, well, by Arthur's stuff there, and here you can do cohomological induction, and here you can do real parabolic induction, or you can go the other order, real induction, and then cohomological induction. It doesn't matter. That's the way you construct. You start with a unipotent Arthur packet, and you do these two kinds of induction in whichever order you prefer, and more or less that's giving you an Arthur packet for G. I think that I will stop here and just leave this. So I did that. I'll just leave the add up and say it's wonderful to be here for this grand occasion, and I'm very grateful for the invitation, and thank you very much.